one here, and because this is important for you guys, okay, some programming tidbits. So one of the things I'm saying here is do not obtain. So for example, here you have to do this this interpolation stuff. Okay, now interpolation, what that means is you will require fine and coarse mesh indices simultaneously. So the question is, how do we run these loops? Do we run fine mesh loops and from that get the coarse mesh indices, or do we run coarse mesh loops and from that get fine mesh indices? Okay, there are two ways of doing it. What I'm saying here is that do not obtain coarse mesh index using fine mesh index. You should always run the coarse mesh loop outside. So what this means is, for example, this is an example of direct transfer and two-point interpolation. Okay, notice that what I'm doing here is I'm running a coarse mesh loop instead of a fine mesh loop on the outside, 1 to NC, number of coarse mesh points. Okay, and here is my formula to extract the fine mesh index. Okay, and then what I'm saying is, here is an example of direct transfer, which says phi fine at node small I is equal to phi coarse at node capital I. Okay, so I have two separate vectors, phi fine and phi coarse. I'm simply using, now this is a one-dimensional example. I'm not using I comma j, just I. Okay, and I'm just transferring that. Here is an example where I do a two-point interpolation. So I'm getting, so if you think about it, here's my coarse mesh, fine mesh. Okay, I want to calculate the value here from these two values. So this is my I plus 1 because this is my I and this is my I plus 1 for the fine mesh and I plus 2. And for the coarse mesh, this is capital I and capital I plus 1. Okay, so we are trying to calculate the value here on that fine mesh, which is that guy, phi fine at I plus 1. That's equal to the phi coarse at capital I plus phi coarse at capital I plus 1 divided by 2. Okay, again, coarse mesh loop is on the outside. Do not do the reverse. Why? Because here is what will happen. You will get into floating point operation problems. If you do the reverse, this is how you have to get the index. So you will say capital I is equal to small I plus 1 divided by 2. That's what this formula gives you. Okay. Unfortunately, that problem will create errors every time you have I which is even. Because you'll get, so suppose small I is 4. You'll get 4 plus 1 divided by 2. 4 plus 1 divided by 2 is not even an integer. And since this is an integer on the left-hand side, the computer is going to come up with an index that's either 2 or 3. Okay? It's totally random. It depends on what computer you're using, what programming language you're using, because it's simply going to approximate a real number with an integer. Okay? So don't ever do this. Always do this. Start with the coarse mesh, get fine mesh indices from that. Okay? Any questions? Okay, so that sort of completes our discussion of the two-grid V-cycle algorithm. Here is a summary of what happens, the flow chart. So you start. By start, I mean you guess your phi. Okay. You perform one Gauss-Seidel iteration on the fine mesh. Okay. And here is an operation count. You have 4 multiplications, 1 division, as you know. Okay. So you're doing that many operations on that many nodes, approximately. Okay. Here's your GMG block now. Normally what we would do is, let me just, from here, we would go directly into convergence check to check convergence, and if it doesn't converge, then we would go back and keep doing this. That's our straightforward Gauss-Seidel. Okay. But now we're sort of taking a detour. Okay. We're not going from here to here directly. Instead, we are going into the geometric multigrid algorithm, So the restriction step is where we transfer the residual, then we smooth the residual on the coarse mesh, then we pass the correction for phi back to the fine mesh, which is the prolongation step. And once we have the new updated solution for phi f, that's when we check for convergence. Okay? So it's kind of a detour. Now let's look at how many operations you have in the detour. In the case that we are talking about, a simple Cartesian two-grid algorithm, restriction has no floating point operations. It's just a direct transfer of the residual from the fine mesh to the coarse mesh. 0 flops. Okay? Error smoothing, if you do one sweep of Gauss-Seidel, it's just one division, as I said. If you're doing multiple sweeps of Gauss-Seidel, then it'll be, first iteration it will be one division times NC, and then it will be basically 4 multiplications, so 5 times NC in subsequent sweeps. Because you'll still do 4 multiplications, 1 division, same as here, but NC number of times, not NF number of times. Remember, NC is 1/4 of NF. Okay, it's a considerably small number. Okay, and then here you're doing one division, because the one division is simply because you have to do that interpolation. Okay, now I'm assuming that all the nodes will require interpolation. In reality, that's not the case. But if all the nodes require interpolation, then you will need one division. That division is either the division by 2 or 4. That's what we're talking about, okay, in the interpolation formula. So that's the number of floating point operations you have for the interpolation or the prolongation step. Okay, so if you count now the number of iterations, you see here this is 5 NF. Okay, and let's even forget the fact that we are doing multiple sweeps. We are doing just one sweep, let's say. Okay, so then you have NC here, and then here you have NF. Okay, so we have basically 6 NF plus NC. Okay, the NC is really negligible compared to the NF. So really what has happened is, if you did straight Gauss-Seidel, you would have that many operations. With the multigrid, you have added one more NF. So that's about, if you come to think of it, about 20 to 25% more operations. Okay. If you're doing more sweeps here, then this could, because now you're going to get 5 NC. 5 NC is pretty much the same as 1 NF. Okay, slightly more. This would increase more. Okay, but so again, it's a question of, okay, if I do more sweeps on the coarse mesh, am I getting substantial gains in convergence? If not, then I'm probably okay doing one sweep. Okay, so there is always a little bit of fine-tuning to be done in these algorithms, which will give you plus minus 1,000 iterations this way or that way. But when you're reducing from 50,000 to 10,000 or even 5,000, plus minus 1,000 this way or that way doesn't really matter. Okay, so that's the operation count. Any questions on that? Yeah.
Why did we use a correction form of the equations when we are doing the restriction?
Because, okay, if you don't do the correction form, so the whole idea of using the correction form is because you're working with the residual, which is the error.
We could just solve for the fine mesh, obtain some values, and use as initial guess for the coarse mesh, and we'll just continue the system.
Okay, so suppose you solve for phi on the fine mesh, and then what do you do with the phi in the coarse mesh? I mean, you can use that as an initial guess for the coarse mesh, okay? But once you get a new solution on the coarse mesh, what do you do to that? All you can add to the fine mesh is a correction. The coarse mesh solution doesn't mean anything. Okay, you have to add back an error or a correction to the fine mesh solution. So what you're doing is, we are following the same philosophy as we used all the time. Every method that we are dealing with, ultimately it's predicting a correction from whatever we initially guessed. Okay, the more accurate the correction, the faster the convergence will be. So this is another method just to get an improved value of the correction. just like the Stone's method where we used a correction. Okay, so that's the idea, that solving it with the correction form is because we want to predict a correction. All right. Now you could probably go back to the math and rework the equations such that you don't do exactly that, but the philosophy will be the same, essentially. Any other questions? The one thing I would also like to mention with regard to Ehsan's question about why corrections, because another reason, remember we talked about this before, that you can pretty much do anything you want with the corrections. Okay? You can't do anything you want with the phi. The phi is phi. Okay? The correction, Multigrid predicts a correction of, let's say, 0.6 somewhere, and you say, well, I'm not going to use 0.6, I'm going to use 6. No one is preventing you from doing that. It doesn't violate any equation, any mathematics. The question is, okay, if you use 6 instead of 0.6, will it converge? That's all. Okay? But if I now take the phi itself, okay, I cannot substitute the fine grid phi with a coarse grid phi. That's an erroneous phi. Okay, because it has huge truncation errors. So, okay, let's talk about the true multigrid algorithm. So this is what we did in the. So this whole thing I'm talking about now is called multigrid scheduling. Okay, this is how you use the recipe for using the different grids. That's what this is. Okay. So in the two-grid algorithm we are talking about, we took the residuals, we calculated the residuals here, and here you basically have a restriction step, and then here you have a prolongation step. Okay, you're smoothing it here, so there's a smoothing operation here, and then you are passing it back. Okay, which is really an update step, and you're getting to the final solution. Okay, so as you can see, this kind of looks like a V, and that's why it's called the V cycle. Okay. Now here is what happens. Here in the coarse mesh, we are using, let's say in the description that I gave you, you're using Gauss-Seidel, right, to smooth out the errors. And I mentioned that it's a good idea to use a tighter tolerance. So what are we doing here? We are actually, again, solving a set of simultaneous equations on a mesh, be that the coarse mesh, but we are actually solving a set of simultaneous equations. So suppose this mesh is 81 by 81. Okay, here we are solving a set of 41 by 41 equations. Okay, that 41 by 41 set of equations has the exact same problems as the 81 by 81 equations. In other words, its large wavelength components is now going to hold up its convergence, because I'm solving it again using an iterative solver. Okay, so the idea in the multi-level multigrid is, well, why don't we use another multigrid to solve that guy? Okay, which introduces now a third mesh level. Okay, and you can keep going down, and this is one of the beauties of multigrid. If you write it in a modular fashion, you can actually call these subroutines recursively. Okay, if you use MATLAB, you won't be able to do it. But if you're using C or Fortran 95, you can call these subroutines recursively, one within another as a block. It's almost as if, this little piece here is one block. So solving this will use another multigrid. Solving the next one will use another multigrid, and so on, until you keep going down. And what people typically do is you go down so deep that at that point, you have maybe, let's say, 100 by 100 system of equations to solve. You use Gaussian elimination to solve it, which drives your error down to zero, identically zero. No convergence error at all at that point. Okay, so on the coarsest mesh, you would finally use a direct solver, because that will give you zero error on the coarsest mesh. Okay, so that's the philosophy people use. So you would go down, keep going down, okay, Ideally, I'm saying. Okay, now there are practical constraints. You keep going down until you get to a set of equations where Gaussian elimination is feasible to use. And you just use that and then come back up. Okay? At all other intermediate levels, you're still going to use your iterative solver, Gauss-Seidel, or whatever other solver you might be using. Okay? Now, of course, to get to the point where you can actually use Gaussian elimination, the number of equations are so small, would require many different mesh levels. I mean, if you start from even 81 by 81, the next one will be 21 by 21, 11 by 11, and maybe by the time you get to 6 by 6, you can actually use Gaussian elimination. Okay, but even that, for a small problem like that, would mean 5 mesh levels. Okay, but that's the general philosophy. Now, of course, everything finally comes down to, is it worthwhile in terms of CPU time? Doesn't matter that even if this gives you convergence in, you go down 10 mesh levels and you get convergence in 10 iterations, you then have to look at the CPU time and say, well, my 10 iterations, is it more expensive than 100 iterations, or is it less expensive than 100 iterations? So there is always fine-tuning and compromises that come into play. But basically, that's the idea that's used in the scheduling, in the multigrid algorithm. So this is the multigrid V cycle. Okay. Now people use all different other, I'm just showing you 2 cycles here. There are other cycles called there's one even which is called the flexible multigrid, where depending on the behavior of the error, you actually either go up or go down. Okay, so they're adaptive in a sense. Okay, so in the V cycle, you basically go down to the deepest level and then you come up, and in the W cycle, you go down, then you come up to an intermediate level, then go down again, and then come up. Okay, if you read through the literature, there isn't any particular preference over one or the other. Some problems work better with this. Some problems work better with this. Most people claim that if you use the flexible cycle, that's the best. Okay, in terms of convergence. But the flexible cycle is much harder to code in. Okay, this one is fairly easy to code in. All right, so that's what the scheduling is all about. Let me show you, I think that's my, so we'll talk about that. Let me just show you some results here. So I'm showing you this, you've seen this already, 2-grid 161 by 161. Now what happens, so here is what the actual V cycle looks like, okay. So basically, these S's represent smoothing and these C's represent corrections. Okay. So here is what a 3-grid algorithm actually looks like, the details. So you're solving on the fine mesh. Okay, right here. Then you're passing that partial solve here. You compute another residual here. You pass it down, and then you're solving it at the next level again. And then you keep updating your fees recursively until you get to the topmost level. Okay, so that's a 3-grid algorithm with some details. But here is what happens with your convergence. Okay, so this one I already showed you, this which took about 5,000. Okay, this guy, this first one. Now this is 5,000 compared to the 50,000 you saw for original Gauss-Seidel for the 161 by 161 mesh. Okay, this is already a huge improvement. But by the time you get to more mesh levels, so here I've used 5. Okay, it's down there. Here's the table: 66 iterations, 0.1 seconds. It's almost, you just hit the enter button on your computer, the answer is there. Instantaneous almost. Okay. It's quite remarkable because, I mean, think about it. 161 by 161, that's 250,000 equations. Okay. 256,000 equations almost. We're solving that in 0.1 seconds. Okay. Did you have a question, Andre?
If you double that number 161 to get 342,
Uh-huh.
is that like 4 times longer, like the 5 numbers? Like how does it scale?
Oh, how does it scale? Okay, so in terms of the scaling, that's a good question. So one of the things, if you look at plain Gauss-Seidel, you probably have looked at it in your homework already. The scaling between two mesh levels is approximately a factor of 4, right? So you need approximately 4 times more number of iterations, okay? One of the remarkable things is, if you look at it, okay, I think I discuss it here somewhere. So we are saying that 161 by 161, okay, requires 66 iterations, okay. If I use the 81 by 81, let me just, let's see. If I used 4 levels, so here's what I'm trying to say. If you use 4 levels and an 81 by 81 mesh, okay, you will get approximately 66 iterations of that type. If you use 161 by 161 and now just increase one more mesh level, you will also get approximately 66 iterations. Okay? What that means is, of course, by using one mesh level, you've done a little bit more CPU. Okay, you've spent a little bit more CPU, but almost linear scaling. So, in answer to your question, if you go, 321 by 321, and you add another mesh level, so 6 levels instead of 5, you will still get approximately 66 iterations. Okay, and that's the beauty of this method. This is why the multigrid method is known as, it is the only method out there. There is no other method like this, which is known as an order n method. Okay, order n meaning the number of iterations scale, or the workload scales exactly as the number of equations. Okay, all other methods, it's a nonlinear power here. For example, one of the other powerful methods, conjugate gradient, for example. Conjugate gradient, I think, has a power of or 3/2, something like that. Okay. The other iterative solvers that you've been using, they typically have a power of 2 there. Okay. This is the only method that gives you almost order n convergence, simply by adding another coarse mesh level. Okay. So that really makes it, so here I have that number that I was trying to guess. This is for conjugate gradient method, 3/2. Okay. So let's just quit this now. Any questions on the performance or any of that? Now, of course, you will get to try some of this for your homework, and for those of you who are interested, you can try more than 2 levels. If you need help, come and talk to me. I'll help you out with that. So one of the questions I talked about is how many mesh levels should we use? The more, the better. Of course, that doesn't mean that you will always get better CPU time. Okay, in terms of iterations, that's what it says here, fewer iterations. The more mesh levels you use, the better performance you will get. Okay, ideally, this is what you would like to do. Basically have in 3D, you have your lowest resolution would be a 3x3x3 mesh, 27 nodes. That's what you want to solve, so that you can do a direct solver on that, Gaussian elimination. Okay, but that's not always possible. So with every new mesh level, you are increasing your overheads due to transfer, interpolation, smoothing, and therefore the CPU time will also increase, and so memory requirement will increase, and so that's something that you have to be have to factor in. Ultimately, at the end of the day, what matters is how much CPU time. Okay. And another thing that is extremely important for the multigrid method is good programming. Okay. If you're doing some redundant steps, it's going to kill you. You've got to really streamline your code so you make sure you're not doing any redundant steps anywhere. Because otherwise what will happen is you'll get fewer iterations, but you will find the CPU time is higher. Okay? That's the problem. So in commercially used multigrid solvers, it's not uncommon to use 10 to 20 mesh levels. All right? So that's our topic of today. Next class, I'll talk a little bit about algebraic multigrid. We'll not go over it in too much details, as detailed as this one, but we'll talk about it a little bit and you'll have some idea. So before we talk about algebraic multigrid, let's talk a little bit about the disadvantages of using geometric multigrid. Of course, we found that it is a powerful method. As I said in the last class, it's the only order n method that's out there. Okay? Which means that it scales linearly with the number of equations. All right. So that's really to a big advantage, but there are some disadvantages, and the disadvantages, one of the biggest ones, is that you have to literally generate multiple meshes for the same problem, which is not always easily done. Okay. Meshes kind of have to obey certain constraints so that you can seamlessly do the prolongation and restriction steps. In other words, the transfer of information between the fine and coarse meshes. Okay, and that's not easily done if you have a complex geometry. I mean, generating one grid itself can be a pretty painful task, and now you're talking about generating multiple meshes and storing all that information. So there's a lot of bookkeeping that's involved in here, and also this method is impossible to use for unstructured grids, because structured grids, so suppose you on a particular edge you specify 20 grid points, okay, and then you say, okay, I'm going to coarsen it now and make it 10 grid points. You can do that, but in an unstructured grid you cannot say that, okay, the mesh will be such that the triangles will be sort of hierarchically linked in a sense. Okay, it's impossible to do. There is no mesh generator which will do that for you necessarily. Okay, so very difficult to use for unstructured meshes, and it's never been tried actually. Okay, because people realized very early on that it would be impossible to come up with something that will work. Okay, and that pretty much led to the idea of algebraic multigrid, with the basic philosophy being that essentially we are using the coarse mesh to smooth errors, specifically the large wavelength components of the errors. So can we somehow use that philosophy but without using multiple mesh levels? Okay, that basically became the motivating force behind the development of algebraic multigrid. Okay, so this algebraic multigrid method doesn't depend or doesn't require multiple mesh levels and can be used with any mesh topology, and in fact it is the so-called plug-in type multigrid method. Geometric multigrid is not a plug-in method because it's dependent on the mesh. Okay, if I gave you an arbitrary set of algebraic equations and said, okay, solve this iteratively, you can't use it using geometric multigrid. The equations that you're solving must have necessarily come out of a structured mesh. Otherwise, you can't use it. Okay? Algebraic multigrid doesn't have that constraint. I can give you an arbitrary set of algebraic equations that came out of some other problem, not even discretizing a PDE. Okay? Just a set of linear algebraic equations. And you can still use the algebraic multigrid method. Okay? So it's truly a plug-in type of method which doesn't require that the equations came out of discretization of a PDE. So how is it all done? Okay, so I'll try to explain here some of the basic ideas with it without getting into too much details. And this is, of course, not one of the methods that you will implement in your homework. So the discussion is at a sort of broad level. Okay, so first of all operations are done at the algebraic equation level. In other words, Right now, for example, you're doing Stone's method where you are assembling A phi equal to Q. Okay. By the time you get there, you don't require any information on the mesh anymore. Okay. All your matrix elements are already there, so you essentially have a system of linear algebraic equations. Okay. And that's where the algebraic multigrid starts its whole process. Okay. It doesn't even bother about where the equations came from. So it starts at the algebraic equation level, but that's what I mean by that. Okay. Meshes, multiple meshes are not used, and you can use it as a plug-in type solver. I already mentioned that. Okay. So here is how it works. This is an example of a simple one-dimensional diffusion equation with just 6 nodes. So suppose I want to use algebraic multigrid on this problem. Okay. So this is my governing equation here. And let's say we have Dirichlet boundary conditions. So we basically have 4 interior nodes. Okay. Now, if I were to do a geometric multigrid, I would generate a second mesh, which would have half the number of nodes, and then transfer information between the fine and the coarse mesh. Okay, as we've discussed before. Here, we have to use the same kind of principle. So if you think about it, instead of 6 nodes, if I have 3 nodes, then I have a coarse mesh equivalent, which basically consists of 3 equations. Okay, so somehow from the fine mesh equations, which I start with 6 equations, I have to derive 3 equations that essentially will represent my coarse mesh equations. Okay, that's the idea. That I'll have 2 sets of equations, 6 in one case, 3 in the other case, and I will do the exchange of information between those 2 sets. Okay. So what I've done here is I've first written out the finite difference equations on the fine mesh. So we have 4 interior nodes, so 4 equations. Okay, boundary nodes, of course, Dirichlet boundary conditions, we don't need those really. They are fixed. Okay, so I have 4 equations here, and I've written out the equations. You're all familiar with this. This is the simple central difference with equal grid spacing. So so this guy here, this delta, okay, that is nothing but your delta xf that we have been using earlier on. Okay, just for shorthand notation, I wrote that. Okay. So first step in the multigrid algorithm is to solve this on the fine mesh to partial convergence. Okay, and then we construct the residuals of these equations and transfer the residuals to the coarse mesh. Okay, and then smooth these errors. That's the basic idea. So how do we do that? Now, in the geometric multigrid algorithm, the coefficient of the coarse mesh is set up by using the coarse mesh geometric parameters. Okay, so once I construct the residual for these guys, R2 up to R4 or R5, and then transfer it to the coarse mesh. Okay, if you recall, if you go back to the geometric multigrid algorithm, we solved AC times phi prime C is equal to R on the coarse mesh, which we got by transfer from the fine mesh, right? This is what we did at the coarse mesh level. This matrix here came out of the fact that we used the coarse mesh. For example, our elements were 1 over delta xc square, 1 over delta yc square, and so on. Okay. Now we don't have that anymore. We don't have a coarse mesh to speak of. So the question is, what are the elements of this matrix? How do we get that? Okay, that's the question I'm trying to answer in this discussion here. So we don't have a coarse mesh. How do we get it? And this is done by a process known as agglomeration. Okay. Agglomeration is just a fancy word for saying we want to combine nodal equations. Okay. Remember, if you have a set of equations, suppose I have 5 equations, you can always add equations 2 and 3, and instead of writing equation 2 and 3, you write equation 2, and then you replace equation 3 by the sum of equation 2 and 3. That's a perfectly valid approach, right? I mean, if I have equations which say x plus, kind of hard to write there because of the resolution, I'll write it here, x plus y is equal to 2 and x plus 2y is equal to 5, Okay, I don't necessarily have to use these equations to solve the system. I can instead use x plus y equal to 2 and 2x plus 3y equal to 7. If I solve that, I'll get the same answer. Okay, so here what I've done is I've simply added these two equations and used that as the second equation instead of the original equation. Okay, so when you have a set of equations, in our case we have 4 equations in this, I can arbitrarily add and subtract equations from each other, okay, to come up with new equations. Because an equation is an equation, both sides balance, so you can add and subtract. So that's the idea being used here. So suppose we want to agglomerate. Now I'll come to why or how you decide which ones to agglomerate. Okay, that's a critical decision you have to make in the multigrid, in the algebraic multigrid, when you construct this course level equations. Okay, should I agglomerate 2 and 3 or 3 and 4? How do I decide? Okay, that's a separate question. We'll get to that later. But let's say we decide that we want to agglomerate 2 and 3, and the coarse mesh node, so to speak, equivalent, we're going to call it node A. All right. So what I do is I start with my fine mesh equations as I've written there, those two. Okay. And let me see if I can, yeah, so that went away. So what I've done here now is I've added those two equations. So you see I have phi2, I have phi2, phi3, and then minus of these guys, okay? And on the right hand side I also added my sources. Okay? Now we are going to make the assumption that since nodes 2 and 3 are being agglomerated, we will assume that phi2 equal to phi3 is equal to phi a. Okay, they have been combined into one node, so their values must be equal. And we are also going to assume that the source term is cumulatively added. The source term in general should be cumulatively added, because if you think about source as, let's say in a heat transfer problem, you have a heat source. The total amount of source you have in 2 control volumes will obviously be the sum of the 2. Okay, so that's the idea here. It's being added. Okay, so when we do that, then we get this equation here. All right. Now notice that I have a phi A, which is on sort of the coarse mesh here, right here. Okay, and then we are left over with these two guys. Okay, the phi 1, which is this one here, and then the phi 4, which is, so essentially what I've done here is I've constructed a coarse mesh equation, which is this whole blob here with 2 adjoining nodes, 1 and 4. Okay, now 4 could have been also combined with 5, and I could have gotten a different blob here. Okay, but that's not what we are doing here. We are just taking one at a time. So right now we have just agglomerated these two guys, okay, without agglomerating anything else. So you can think of, okay, instead of 4 nodes, I now have 3 nodes. So it is sort of a coarse mesh equivalent. Okay. Now you could, as I said, also agglomerate 4 and 5 and reduce it further. Okay. But this is what this is showing is, so now I can also, in addition to this, I can say that, okay, if I don't agglomerate any further, then my phi 1f is the same as phi 1c, and my phi 4f is the same as phi 4c. So now I have a coarse mesh equation essentially. Okay. All right. Now, what's interesting is, I mean, this is kind of straightforward what we just derived here, but then what do we get out of all this? What we get out of this are some formulas. Okay. And this formula says that the diagonal of the new or agglomerated node is the sum of the diagonals of the individual nodes, meaning the fine mesh nodes, plus the sum of the link coefficients connecting individual nodes. Okay, and I'll demonstrate that to you in a moment. And then the source of the new agglomerated source is the sum of the sources of the individual nodes. Okay, these are 2 important formulas we get out of this derivation that I showed you on the previous page. Okay, and here is how it works. So these are the 2 equations we started with. Okay, so if I now apply this formula here, this guy, okay, so sum of diagonals of individual nodes, let me get this out of the way so we can see clearly. Sum of the diagonals of the individual nodes is clearly 1 plus 1. Okay, that's 2 right there. All right, because the diagonals have 1 on both equations. Then we are saying sum of the link coefficients connecting individual nodes. Okay. So link coefficient from 2 to 3 is right here, negative 1/2. Okay, first equation. And then you have also connecting from 3 to 2, okay, is negative 1/2. So this link coefficient that you have, see, remember this is the equation for node number 2, okay? And to its right you have node number 3. This -1/2 is the link coefficient that is telling you how node 2 is connected to node 3. Similarly, in the next equation, we are constructing the equation for node number 3, and this -1/2 is telling you how 3 is connected to 2. Okay? Now, in a diffusion equation, those coefficients are usually always equal because diffusion goes, it's unbiased. It goes both ways. All right? If you had a flow equation, for example, if you're looking at an advection diffusion equation, you would find that one of the coefficients is larger than the other depending on the direction of the flow. Okay? Now, these link coefficients, they're called link coefficients because they link the nodes to each other. All right? And their magnitudes actually represent how strong that link is. So suppose this in this one of these links, suppose this link was 50 and this link was 20, then that means node 2 is going to be influenced by node 3 a lot more strongly than it would be influenced by node 1. Okay? That's what it means. And it comes from the physics. So in a heat equation, for example, I'll show you let me just hold off on that discussion. I'll show you that in a moment. These coefficients actually are dictated by the physics, how strongly these links show up as, okay? How strong they are. Anyway, let's get back to the formula. So we have this, okay? And same thing as I said from 3 to 2, -1/2. So now if I apply the formula, the diagonal of the new node becomes 2 -1/2 -1/2. So I'm applying this whole formula here, okay? And that's a 1. All right? So that's what you see here. This diagonal is 1. Okay? Everything else remains unchanged except the source term. The source term also, of course, got added. Okay, so let me just go back here and show you. So these two got added into that one. Okay, because we said that the agglomerated source is the sum of the sources of the individual nodes. So S2 and S3 simply got added to give you SA. Okay. So that's how you form the agglomerated equation. Now it's easier said than done because you have to have proper logic which will say, okay, so for example, I have agglomerated 2 and 3. So you have to remove 2 and 3 from the complete list of nodes that you had so that, 3 again doesn't get agglomerated with something else. Okay. And then you have to look at the remaining ones and see which 2 next ones are best to agglomerate and so on. So there is a pretty complex logical flow to this, how you pick the nodes to agglomerate and how you finally assemble the equations. Okay. For example, if you agglomerated 4 and 5 in addition, okay, if I go back here, these two guys, okay, then not only will you have a new equation for that, these equations here will also change because you will no longer have 4. You will basically have another node which you can call, let's say, B. Okay, so you will have node 1 to the left of A, and then you will have node B to the right of A, And so this equation will also get modified. So agglomeration not only changes the equation for that particular node which you agglomerated, it may also change the equations for the neighboring nodes. Okay? So it's a little bit complex in that sense. Okay, so then comes the question, why did I decide that I want to agglomerate 2 and 3? What determines which ones I want to do? Why do I want to do 2 and 3 and not 3 and 4? Okay? So that decision is influenced by the strength or magnitude of the link coefficients connecting 3 to 2 versus 3 to 4. Which one do I want to do? Do I want to do this or do I want to do that? Okay? And this is what I was talking about. So in this case, it's half on both sides. So you can see connection to 2 has a minus half, connection to 4 has a minus half. So equal probability. Either one is fine. Okay? But that's usually not the case when you look at typical physical problems. So for example, if you have, let me just go down here a little bit, or let me clear this and work this out for you. So suppose you do a heat conduction problem, okay? Then you might get something like, now this will happen with actually the you might get a nodal equation which looks like that. This what I've written here is when you use the finite volume method, okay? But similar equation in a sense. You can see there are two phi i's here. So if I take k equal, then you will basically get phi I minus 2. Actually, there's a square here. You will get phi I minus 2 phi I plus 1 minus 2 phi I plus phi I minus 1 divided by delta square equal to source, which is the basically the finite difference equation that we have been working with. But this is just an example of the type of equation you might get. Okay, so here if you look at it, okay, you have different link coefficients. So for example, in front of the phi I plus 1, you have a ki plus 1 over delta I plus 1 square, and in front of, so this is what pre-multiplies phi I plus 1, and then you have that multiplying the I minus 1. Okay, so these two link coefficients, this one and this one, they're not equal. Okay, if I draw a little picture here, if this is my I and I minus 1 and I plus 1, these represent how strongly these nodes are connected to each other. Okay, now think about it. We are basically looking at the ratio of k to delta, delta being the spacing. Okay, so when will that quantity be large? That quantity can be large either when k, the thermal conductivity, k is the thermal conductivity in this case, if that's large, or the delta is very small, right? So what does that mean? Let's consider the case where k is very large. So suppose the thermal conductivity between that node and that node is much larger compared to the thermal conductivity between that node and that node, okay, then this will dominate. What that means is that the temperature of between I and I minus 1 will be much closer than the temperature between I and I plus 1. As you know, temperature gradient goes inversely as thermal conductivity. Okay, if you have a copper rod, the two ends of the copper rod will be much closer in temperature than if you have an insulating material, which will have a large temperature gradient typically. Okay, so the higher the thermal conductivity, the closer the temperatures will be between those 2 points. So what that's telling me is that I should really agglomerate these two guys if my if this guy, ki over delta I, is larger than ki plus 1, square, over delta I plus 1 square. I should agglomerate these two guys. Why? Because the link coefficient here is larger. The physical reason for that is the temperatures I and I minus 1 will be very close. So that assumption that we made of, remember in the previous slide we said phi3 equal to phi4 equal to phi A. Okay? That assumption becomes more justified. If these two temperatures, this one and this one, are close, then it makes perfect sense to agglomerate them and make them one node. Because there's nothing going on, in terms of, there's no difference between those 2 points, essentially. Okay? Whereas this one and this one, they are off, their temperatures are quite a bit different, and therefore it's better to keep them separate, not agglomerate them at all. Okay? So the whole strategy of which equations to agglomerate depends on the strength of these link coefficients, because they are essentially telling you how strongly is the bond between two adjacent nodes or control volumes, okay, whichever way you look at it. Okay. The other option, as I was saying, there are 2 ways to do it. One is you look at large K. Another option would be, let's say delta in one case is much smaller. Okay, so if this delta is much smaller than that delta, then that means these 2 nodes are physically much closer, and therefore it makes much more sense to again agglomerate them. Okay, so either way you apply the logic, that ratio basically dictates which ones you want to agglomerate. Okay, in general, it doesn't matter what the PDE is. Your link coefficients will tell you how strong the connection between 2 nodes are. No matter what the physics, it could be flow, it could be diffusion, it could be anything. Okay. Any questions on that? Okay, so let me see if I can get rid of that. Okay. Oops. I guess I have to. Sorry about that. I'll just get that and then, yeah. Okay, so as I said here, the link coefficients physically represent the strength of communication. So in a heat conduction problem, strong link coefficients between 2 and 3 would indicate that 2 and 3 communicate strongly by conduction and are likely to have similar temperatures, and therefore this approximation would be more valid. Okay. And this is the example that I was giving, that you have to look at the ratio of K over delta, okay, right here. So that's the logic we follow. And this rule can be applied to any general PDE without consideration of what the link coefficient actually represents physically. Okay, so that's what people do. They compare link coefficients between neighboring nodes, and then they say, okay, this link coefficient is the largest, so I'm going to agglomerate these 2. Question?